Hello friends, welcome to my physics class. Now today's discussion is on amplitude and velocity resonance. Now for amplitude resonance we know that the amplitude in steady state is of this form. Okay, A equal to f0 by m root over omega square minus p square whole square plus 4b square p square. Now to find the frequency at which amplitude resonance happens, basically the denominator has to be very low, right? Now how to find out the position, means the frequency at which this will be the minimum. For that we require this condition d dt p, because p is that variable, p is that external force frequency, right? Frequency of the external force, so that will be varying. What is omega? Omega is the natural frequency of the system, so that's why we have to take derivative with respect to p. Now if we do that, then we can find out the frequency. Now if we do that derivative d dt p, then after this calculation you can see we are getting p equal to root over omega square minus 2b square. So this is the amplitude resonance frequency. Okay. Now if we plot the amplitude resonance curve, means in y-axis there will be the amplitude and x-axis there will be the variable p, and the center is omega, that is the natural frequency. So the curves will be like this. So when the b is very small, you can see it is very sharp, width is very small. Then if we increase b, the amplitude decreases and the width of the curve will be more. Okay. So now you can see the frequency at which the amplitude resonance happens, means the amplitude will be maximum, that is shifting from omega, because the expression you can see root over omega square minus 2b square. So if b increases, p will be shifting from omega. So that's what happened here. When the v is very small, for example b is 0, then p will be omega, right? So please remember that for amplitude resonance, the frequency at which the amplitude will be maximum, that is different from omega. Now for velocity resonance, the steady state solution we got x equal to a prime e to the power I pt, where this amplitude a prime form is small f0 root over omega square minus p square whole square plus 4b square p square. So small f0 is nothing but capital F0 by m. Now to get the velocity, we have to take derivative of x with respect to the time. So if you do that, we will get this form. Now you can see the velocity we are getting imaginary number, imaginary form. Now we know that velocity cannot be a imaginary number. For that, to get the amplitude of the velocity, we can use this form root over dx dt star dot dx dt. Dx dt star means we have to take the conjugate of dx dt. So if you take the conjugate, then that I term will be minus I. So in the bracket it will be minus ip, and in the exponential term it will be e to the power minus ipt. Then if we take the simple multiplication of this conjugate of dx dt and the original dx dt, then if we take the root over of that, then we get a prime p. So it is a very simple calculation. Whatever I told the process, you if you follow, you will get this. Then you know the form of a prime, we will get f0 p divided by root over omega square minus p square whole square plus 4 b square p square. Okay. So this is the amplitude of velocity, the magnitude of velocity. Okay. So now to find out at which frequency the velocity will be maximum, so we what how we can do that? So here the form, in if you see the form, in the numerator there is a extra p term, right? So now if I take it to the denominator, and if I insert it within the root over form and then again that square form, then it will be f0 divided by root over omega square by p minus p then whole square plus 4b square. Now if you see, if we make it 0 we then that square term, that is the omega square by p minus p, that this term, then we will get the maximum value of velocity. So this is the condition of resonance frequency, and we are getting that the p equal to omega. So at p equal to omega the velocity resonance happens. So this is the resonance frequency. Okay. Now if we plot the velocity resonance curve, means in y-axis there will be the velocity amplitude, and in x-axis that will be the variable p, and the center, that is the omega, the natural frequency of the system. The condition we know that p equal to omega, right? So it is independent of b. So whatever b is, the position of the peak will be at the omega position. So that's why the plot is like that. Now we will discuss an important term, that is sharpness of resonance. Here I will not do any detailed calculation for this, rather we will try to understand it from this curve only. Now here you can see I have indicated two frequencies, that is omega 1 and omega 2. So these frequencies are the frequency at which the velocity will be the maximum. So this is the called the frequencies of velocity at half maximum. Okay, so this is basically nothing but the bandwidth of this velocity resonance curve for a particular b. Now sharpness of resonance is quantified like this, it can be proved omega by 2b. So this 2b value is nothing but that bandwidth delta omega. Okay, and this is also exactly equal to the quality factor of the system in this force vibration case. Okay, so if the b is small then it will be very sharp. If b is large, sharpness will be low. And you know that if b is low then the amplitude of this velocity will be very high. If b is high then amplitude will be low, it will be very broad. So the sharpness of resonance actually measures, can be measured by this form. Okay, now I will summarize the whole things showing these differences between amplitude resonance and velocity resonance. So the first point you can write, the amplitude becomes maximum, and for velocity resonance velocity becomes maximum. Now second point you can write, at p equal to root over omega square minus 2b square amplitude resonance happens, and for velocity resonance at p equal to omega velocity resonance happens. In the third point you can show the two different plots. In amplitude resonance you can see clearly it is showing that the patterns for different b it is shifting from omega, right? But for velocity resonance it is independent of b, and for any value of b, p equal to omega is the condition, that's why the peak is at exactly omega. Now the fourth point you can write, for amplitude resonance the potential energy becomes maximum, and for velocity resonance it is related to kinetic energy, so kinetic energy will be maximum. Now this question is very important for your exam purpose, so please note it down very carefully. Okay, thank you, best of luck.